Hello, today we look at this definite integral. It says integral from 0 to 2 over 3 of the root of 4 plus 9x squared dx. Actually, to do this integral, we have two options. Either we can use a trigonometric substitution or a hyperbolic substitution. And we are going to recall the hyperbolic and the trigonometric substitutions that are directly linked with this question. The first one is the Pythagorean identity, 1 plus tan squared theta equals sec squared theta. And the second is a hyperbolic identity, which is 1 plus sine squared u equals cos squared u. Actually, when you have integrals in which there is either a sum or difference of two squares in the radical sign, you can use either a trigonometric substitution or a hyperbolic substitution, as the case may be. For the case where there is sum of two squares in the radical sign, like we have in the question above, we either use 1 plus tan squared theta equals sec squared theta, or 1 plus sine squared u equals cos squared u. You consider there is a relationship between these two identities and the sum of squares that we have in the radical sign. The left hand sides of the two identities also have a sum of squares, and that is why they will be appropriate for this substitution. And so in this case, where there is sum of two squares in the radical sign, you have the option of either using doing the substitution x equals a tan theta, or doing the substitution x equals a sine u. Of course, there are other cases that you may need to know too. In the case where we have, instead of sum of two squares, difference of two squares in the radical sign, if the difference of the two squares is such that the term in the square of the variable is positive, then you either have to use x equals a sec theta or x equals a cos u. These other substitutions can be arrived at easily by rearranging these other two identities so that they take the form in the radical sign there. Then lastly, where the difference of two squares is such that the term in the square of the variable is negative, you would have to use conveniently a trigonometric substitution, which is x equals a sine theta. Now in this video, I'm going to do the two substitutions so that we see the tricks that are involved in each case. We begin with the case where we are using a trigonometric substitution, and the integral again is here. We note that in the radical sign we have sum of two squares, so the substitution we have to use is 3x equals 2 tan theta. In the case where the coefficient of x squared is not unity, we have to be very careful so that our substitution will tidy up well. So the best practice is to find the square root of the term in x squared there, which should give 3x, equals the square root of the constant term, which is 2, or the coefficient of the trig function that we are bringing should always be the square root of the constant term in either the sum or difference of two squares that you are supposed to do your substitution. So from here we need a substitution for the x, which we can obtain by differentiating both sides of this equation with respect to theta, so that we now get dx equals 2/3 sec squared theta d theta. We also need to change the limits of the integral to reflect the new variable, and if we start with the lower limit, when x equals 0, tan theta equals 0, and it would follow from there that theta would be tan inverse of 0, which is 0. For the upper limit, when x equals 2/3, tan theta equals 1, and so theta will be tan inverse of 1, which is 45 degrees or pi over 4 radians. We can then proceed to do the substitution, where the integral now becomes integral from 0 to pi over 4 of the root of 4 plus 4 tan squared theta times 2/3 sec squared theta d theta. Remember, 2/3 sec squared theta d theta is the replacement for the x, while 3x is being replaced by 2 tan theta. So 9x squared being the square of 3x, it means that that term will now be replaced by 4 tan squared theta. In the next step, we factorize 4 in the radical sign so that the square root of 4 would be 2, and 2 would multiply 2 over 3 to give 4 over 3. Then 1 tan squared theta is sec squared theta, and the square root of sec squared theta is sec theta. The sec theta obtained times sec squared theta will now give sec cubed theta, so that the integral now reduces just to 4 over 3 integral from 0 to pi over 4 of sec cubed theta d theta. So in order to integrate sec cubed theta d theta, then we need to break it down into the product of sec squared theta and sec theta, so that we can then use integration by parts in evaluating the integral. So to start the integration by parts, we let u to be sec theta, so that u prime would be sec theta tan theta, and we also let v prime to be sec squared theta, so that the integral of sec squared theta would give v as tan theta. The next step now, we proceed to use the integration by parts formula, where the first term has to be uv, and u being sec theta while v is tan theta. We have sec theta tan theta as the first term there, minus the integral of v u prime d theta, and v is tan theta while u prime is sec theta tan theta. So in the next step then, we proceed to simplify the integral at the last term, where tan theta times tan theta will become tan squared theta, and tan squared theta is sec squared theta minus 1. So in the next step then, we have the substitution of this first term, of the limits in this first term, where the substitution of the upper limit pi on 4 follows that sec pi on 4 is 1 over cos pi on 4, and cos pi on 4 is 1 over root 2. So sec pi on 4 should then be root 2 times tan pi on 4, which is 1. It just gives root 2. The substitution of the lower limit gives 0, because tan 0 is 0. In the next step, we proceed to expand the integral there. So sec theta times sec squared theta will give sec cubed theta, and sec theta times negative 1 will give negative sec theta, times the negative sign, they will now give positive sec theta. And at this point, we note that this integral is identical to the one we are seeking to get, so we send it to the left hand side. We'll add to the one there to give twice the integral from 0 to pi over 4 of sec cubed theta d theta equals root 2 plus the integral of sec theta d theta, which actually gives ln of sec theta plus tan theta. And we have to execute the limit substitution from 0 to pi over 4. So proceeding with the substitution, then we would have that sec pi over 4 is root 2 and tan pi over 4 is 1. So we have ln of root 2 plus 1 as the result of the substitution of the upper limit, while the substitution of the lower limit gives 0, because sec 0 is 1 and tan 0 is 0, but then ln of 1 is 0. So the substitution of the lower limit generally gives 0. So from this step, we can see that the integral from 0 to pi over 4 of sec cubed theta d theta becomes half into root of 2 plus ln of root 2 plus 1. We can then go back to our integral, which we abandoned at the step where we had to evaluate 4 over 3 integral from 0 to pi over 4 of sec cubed theta d theta, and proceed to replace the integral of sec cubed theta, which we are just from getting, as half into root 2 plus ln of root 2 plus 1. And upon simplification, we have that the integral from 0 to 2 over 3 of 4 plus 9 x squared dx equals to third into root 2 plus ln of root 2 plus 1. The next approach is the one where we are using but a hyperbolic substitution, and again the integral being this, we can use 3x equals 2 sin u. Again, we have to find the square root of the variable term and write on the left hand side of our suggested substitution, and then the square root of the constant term would be the coefficient of the appropriate hyperbolic function, just like we did with the case of the trigonometric substitution. And we proceed to get a replacement for the x, which should be 2 over 3 cos u du when we differentiate both sides of the substitution with respect to u. And we also have to change the limit to reflect the new variable. For the lower limit, when x equals 0, sin u equals 0, and u is sin inverse of 0, which is 0. For the upper limit, when x equals 2 over 3, sin u equals 1, and u is sin inverse of 1. Proceeding to replace the variables, then we have that the integral becomes integral from 0 to sin inverse of 1 of the root of 4 plus 4 sin squared u times 2/3 cos u du, and we factorize 4 in the radical sign there to have 4 into 1 plus sin squared u times 2/3 cos u du. The square root of 4 is 2, so we can multiply 2/3 by that 2 to have 4 over 3, and then 1 plus sin squared u is actually cos squared u, which the square root of cos squared u would give cos u, and then cos u times cos u will now give cos squared u du. At this point, it is difficult to integrate cos squared u directly, so we need to bring in another identity to help. The identity that 2 cos squared u minus 1 equals cos 2u, which we can then make cos squared u the subject to have half into cos 2u plus 1. So we can then proceed to replace cos squared u by half cos 2u plus 1 in the integrand, and in the next step then 4 over 3 times half would give 2/3, and the integral of cos 2u is half sin 2u, and the integral of 1 with respect to u is u. In order to substitute the upper limit, we have to be very careful. It has sin inverse of 1, so the best practice would be to express sin 2u completely in terms of sin u, so that we can be able to do the substitution without complications. Then we note that sin 2u is 2 sin u cos u, so that the 2 cancels the half, and we have sin u cos u, which we can now write the whole expression as sin u into the root of 1 plus sin squared u, because cos u is equal to the root of 1 plus sin squared u. So we proceed to replace that expression in the integral, and then substitute the upper limit, so that we have sin of sin inverse of 1 times the root of 1 plus sin squared of sin inverse of 1 plus sin inverse of 1 when you do the substitution for the upper limit in the simplified expression, and then minus 0, because when you substitute 0 you have half sin of 0, which is 0 plus 0, so the substitution of the lower limit gives 0 entirely. Then in order to simplify, we note that sin of sin inverse of x will always give x, so in the next step the integral simplifies to 2 over 3. Then we have sin of sin inverse of 1, which is 1 times 1 plus 1, which gives root 2, plus the last term, which is sin inverse of 1. In order to simplify sin inverse of 1, we start by noting the logarithmic form of sin inverse of x, which is ln of x plus the root of 1 plus x squared for all values of x. So using this logarithmic form, we can express sin inverse of 1 in logarithmic form as ln of 1 plus the root of 2. And so we can now simplify our integral to have integral from 0 to 2 over 3 of the root of 4 plus 9x squared dx equals 2 over 3 into root 2 plus ln of 1 plus root 2, which gives the same result as we had when we did the substitution using a trigonometric function. Okay, if you are new in this channel, please consider subscribing so that you do not miss any of our videos. Also ensure that you activate the notification bell so that you don't miss any of our publications, because we publish at least a video per week.